All right, let's start the second part of today's lecture. So it's Introduction to MapReduce and Spark. I know usually when we finish introducing Hadoop and HDFS, we should dive into the detail about MapReduce. But I choose another way. So my plan was I will briefly introduce MapReduce, very briefly, and then we turn into Spark. MapReduce actually motivate us to use Spark. Okay, then we will introduce RDD in Wednesday's lecture as well. Then we will go back and discuss more about MapReduce. So that's hopefully on week 4. And week 5, we will discuss nearest neighbor search in high-dimensional space. Then in week 5, we will also release our project 1. So it is about the implementation of a nearest neighbor search algorithm on top of PySpark using MapReduce and RDD. So yeah, that's pretty much the plan. Now, in order to make you appreciate Spark, we need to give a brief introduction about MapReduce first. So that's why this 1 hour is about introduction to MapReduce and Spark. Now let's first look at the motivation of MapReduce. So assume that we're doing this word count thing. So this task, the goal is to output the number of occurrences for each word in the dataset. This task looks boring, but it is it is not. This is Google's n-gram Vera, where Google counted like how the phrases have occurred in a corpus of book over decades, right? And then the number here actually shows something. For example, in this figure, as you can see, it shows the trend of frequency of different phrases here. So for example, child care, before 1970, it is rarely used, but in 2000, it is like the most frequently used word or phrase in books written in English and published in the United States. And you can see a lot of interesting facts, all from the count of n-gram, or the count of phrases, or the count of words. All right, so let's look back at our task here. So we're going to output the number of occurrence for each word in the dataset. So the dataset is D. The naive solution, where the pseudocode here. So this is the function name. This is the function name. So we build a new dictionary named H, and for each word in D, we add 1 to HW. Okay, and so this is for counting, and for each, and finally for the output, for each W in H in the dictionary, we print the word and its frequency. All right. So this is output. Now the problem of the naive solution is it needs to go through the whole dataset and do the counting for each and every word. Now consider the example that we have shown before, the Google Ngram Viewer project. So there could be millions or thousands of thousands of millions of books there in the corpus, in the data set. And if you go through them using a single machine, that would be a large consuming of time. And also, now since we have learned HDFS, we know that we probably store this huge amount of books in HDFS, means in different data nodes. So like data nodes here, and if the client want to do this word counting thing, it would read the blocks from different data nodes and do the counting, which will also bring a large amount of network communication cost as well. Now, since we already have a large amount of data nodes which stores the blocks of the file, how can we speed up the whole procedure? Say, make use of multiple machines, or even better, if we can make use of multiple data nodes. I mean, storing files only use their hard disks, so their CPUs and memories are free, right? So the immediate idea was is to split your task into a set of subtasks and assign to different workers. So each worker will receive the task and output the result, and then the results are aggregated as the final result of the whole task. Now, if we consider the background of using HDFS, then we do want that, because the data is stored on different data nodes, we do want that each data node could handle the data block that is stored in it. So we do not need to transfer data block from one machine to another. So here we do want that task 1 contains data from block 1, and this is the data node 1 that contains the data of block 1. And in this case, you would have more than 3 subtasks corresponds to different blocks and for different workers. And then the results of the subtasks are aggregated to the final result. So that is what you or what we intend to do. However, there are several problems or issues in this scenario. For example, the data reliability. I mean, when any of the machines are not working or have lost part of the data, you need to handle this. For example, find data from the data replications from other data nodes, or you need to recover or reconstruct the data, right? And equal split of data, because we divide the data into smaller chunks so that we can assign each machine with a chunk as a subtask. So we do want that these parts or these chunks are equal large, right? So that there's no individual machine that will be overloaded or underutilized, right? And delay of worker. So if any of the machines delay the job, especially for the machine that lies on the critical path, yeah, I think you all know critical path because you are required to take the project manager course, management course. Yeah. So yeah, if the machine lies on the critical path of the task, so the whole work gets delayed. So how do you handle such kind of case, right? And failure of worker. What if a machine cannot calculate the results, cannot output the results? So we need a method to ensure this fault tolerance capability of the system, so we won't be hugely affected by such case, right? And aggregation of the results. It's how to collect and aggregate the results from the subtask results from different workers and generate the final output. So that would be also could be a problem. Right? If in traditional way of a parallel and distributed processing, we need to handle them all by ourselves. This is not a good news because we need to put a lot of efforts on this side tasks to ensure the whole program can execute it correctly, right? So these tasks occupy the time that we could use on the core task at the first place. So what we need is a method or a framework that can kind of handle these tasks or problems for us, so we can focus on the real task itself. And that is the motivation of MapReduce. So MapReduce is a programming framework, right? So it's a framework that allows us to perform distributed and parallel processing on large datasets in a distributed environment. And if we're using MapReduce, then there's no need to bother about the issues like reliability or fault tolerance, etc. Right. So MapReduce offers the flexibility to write code logic without caring about the design issues of the system. So apparently, MapReduce is exactly what we need to address all the problems listed here. All right, and there are two things that we are caring about. One is the logic of design a MapReduce program or write a MapReduce code. And the other is how does MapReduce handle these issues like reliability or fault tolerance or delay of worker, such kind of issues. Right. So in this course, we will only focus on the programming logic or the programming framework of MapReduce. We will not focus on the detailed implementation of MapReduce itself. All right, and well, MapReduce, or more specifically, Hadoop MapReduce, is an implementation of MapReduce, which is a computing paradigm from Google, right? And yeah, Hadoop MapReduce is an open source software. Okay, and in this course, we will write our MapReduce programs in PySpark, which is on top of Spark. Okay, we will we will show the motivation of using Spark rather than Hadoop to write our MapReduce tasks. Okay. So in order to write a MapReduce program or use MapReduce to implement your task, so the MapReduce consists of map and reduce. So only these two operations. So for map, or say mapper, it reads a block of data and produces a key value pairs as intermediate outputs. These outputs will be the input of the reduce part, or say the reducer. So for the reduce part, it receives key value pairs from multiple map jobs, and it aggregates the intermediate data tuples to the final output. So the interesting thing here is that, well, it looks like MapReduce is pretty easy because you only have map and reduce. And the functionality of map and reduce is also clear and seems easy to implement, right? But on the other hand, if you think from a different perspective, whenever you want to use MapReduce to do your task, you need to convert your task into a set of map and reduce operations. So yes, MapReduce is easy, but it also limits your creativity. Means your design has to follow the idea of MapReduce and has to be split or converted into a set of map and reduce operations. And in this NICE 313 course, our goal is to show you different examples of how we do perform different tasks using a MapReduce. Okay. So for today, as an introduction to MapReduce, let's look at the most classic and easiest MapReduce jobs. So the word count again. And we will use this example to show the overall MapReduce. Now let's look at this step by step. All right. So first of all, input. Right. So input. This is the input data or the file to be processed. So in this step, the sample file is input to MapReduce. In our example, the sample file is like this. Okay, so there are 3 lines. Here comes the second step, which is splitting. So in Hadoop, Hadoop splits the incoming data into smaller pieces called splits. So as the example here, the input file is divided or splitted into 3 parts. Each part is one line from the input file, like a Dear Bear River or Kaka River or Dear Car Bear here. Okay, it is note that this is just an example, but in reality here the splitting is usually based on blocks. Okay, on blocks. Now for mapping, in mapping, each split is fed to a mapper. So this is a mapper here, right? And so the mapper is a map function containing the logic on how to process the input data. So in our example, the map function will contain the logic to count the occurrence of each word and each occurrence is captured as a key value pair, like a deer 1, beer 1, and river 1, such kind of key value pair. So the key is the word, and the value is the currency. In the mapping file, the value is all the values are 1. So sometimes there is a combine here, but in today's example, we will not discuss this one. We will leave it to the later discussion. So let's look at shuffling. It also called shuffling and sort. So in this step, the outputs from all the mappers is shuffled, sorted to put them in order, and group before sending them to the next step, which is reducing. So in the reducing, we aggregate the outputs of mappers using the reduce function. So in our example, we aggregate the count of the words and produced the key value pairs. For example, the beer 2, car 3, deer 2, and river 2 here. And finally, the output of reduce step is written to a file in HDFS. So remember, this is important as the result of this MapReduce process will be written into HDFS. Remember, in Hadoop, the final results will always be written into HDFS. And soon we will see the problem of this scenario. So as we mentioned before, in MapReduce, all you need to do is to write a map and to write a reduce. There are 2 methods, 2 functions. That's all for MapReduce. And in this word count example, the pseudocode of map and reduce functions is like this. So for map, the input is the, which is a split of the data or a block of the data. And what the function doing is for each word in D, output a key value pair. So W is key and 1 is value. This is map. And for reduce, the input is T, which is a word, and counts, which is a list of values or a list of counts. So in reduce function, we use sum to record the total number of occurrence of T. So what we do is for each number in counts, we add it to sum. And as a result, we output T and sum as part of the final results. So for our word count example, that is MapReduce, the pseudocode of MapReduce. So it is, as you can see, very easy, right? However, as I said, the difficulty of designing a MapReduce framework or a MapReduce program depends on the task itself. So word count is easy, does not mean all the MapReduce code would be easy. Now let's look at the advantages of MapReduce. So in MapReduce, we divide the job to several subtasks and assign to multiple nodes. And each node works with a part of the job simultaneously. So it is a parallel processing. So MapReduce is based on this divide and conquer paradigm, which made us to process the data using different machines or different nodes. So as a result, I mean, since the data is processed by multiple machines instead of a single machine, the time taken to the time taken to process the data gets reduced. So that is the first advantage of MapReduce, which is parallel processing. So the second advantage of MapReduce is data locality. If you still remember, I mean, about half an hour ago, we're talking about data locality when we compare the difference between replications and erasure coding. So basically, the idea of data locality is instead of moving data to the processing unit, we are moving the processing unit to the data in MapReduce framework. So in the traditional system, we used to bring data to the processing unit and process it. But when the data grew and become very huge, bringing this huge amount of data to a processing unit will bring a couple of issues. For example, moving huge data to processing unit is costly because of the communication, the network communication, right? And the processing takes time as the data is processed by a single unit, a single machine, which this becomes the bottleneck. And also, I mean, the master node, which receives all the data and do the processing, it can get overabundant, and it is possible that the master node fails, so the task it fails as well. Now in MapReduce, we bring the process unit to the data, so we kind of overcome the above issues, right? So as you can see, bringing the processing unit to the data allows us to have a couple of advantages. For example, it is very cost effective to move processing unit to the data. The processing time is reduced as all the nodes are working with their part of the data in parallel. And every node gets a part of the data to process. So there is no chance of a node to get overburdened. All right, so we will discuss more on MapReduce probably this week, later this week, or next week, definitely. But we are not going to discuss MapReduce for now. Okay. So now we look at Spark. So why we need Spark, right? So the motivation of Spark actually comes from MapReduce, or mainly comes from MapReduce. All right. So MapReduce, as we just introduced, it greatly simplified big data analysis on large, reliable clusters. So MapReduce is great at one-pass computation. What is one-pass computation? Just like word count. So basically, you use one map and one reduce, and you finish your job. So that is one-pass computation. However, I mean, as soon as it got popular, users wanted more. It is very common, right? So basically what users wanted is a more complex multi-pass analytics. For example, in machine learning, when you train a model, usually you won't train it once. You need several, usually thousands or even 10 or hundreds of thousands iterations. So in each iteration, you need process on the whole data set for once. So for each iteration, it is one pass. So for the whole procedure of training a machine learning model, it is multi-pass. Right. And also the users wanted a more interactive ad hoc queries. For example, the users want to know the nearest, the most similar text, let's say, to the query text. So this kind of queries comes time by time. Whenever a new query come in, you are supposed to scan the whole data set to get the result to that query. And when multiple queries comes in, you need to do it again. And also the users wanted a more real-time stream processing. For example, the healthcare, in healthcare domain, they use real-time analysis to continuously check the medical status of the patients. Right? The government agencies use real-time analysis to on the field of national security to monitor terrorists, right? And for example, stockbrokers use real-time analytics to predict the movement of the stock portfolios. So all these tasks need the system to react very quickly, right? So for MapReduce, as a general programming model, MapReduce is more suitable for one-pass computation on large dataset. And it is hard to compose and nest multiple operations in MapReduce. Therefore, there's no means of expressing iterative operations using MapReduce. And from the perspective of implementation in Hadoop of MapReduce, we know that all the datasets are read from disk, then stored back onto disk. As if you still remember that I've emphasized before, every time you've got the final results of a MapReduce process, you will store the result back onto the disk, to the HDFS. And also in HDFS, all the data is usually triple replicated for reliability. So anytime you store back the results onto the disk, you need to create 2 more replications for that result. So it is kind of a waste of space and time. So let's see 2 examples to show the problem of Hadoop MapReduce when handling different kind of tasks. So this task is a typical machine learning task where the input, you do the iteration. For each iteration, you need read from HDFS and write the result to HDFS. And for the next iteration, you need to read from HDFS again and write to HDFS, and so on and so forth. For most of machine learning tasks, in each iteration, you will not only read the intermediate results from a previous iteration, you also read data from the input again. And the second example is clearly about is an example of queries, processing queries. So basically, for different queries, you will always need to read HDFS, right? So apparently, Hadoop MapReduce is sometimes called slow because of replication serialization like this and like this, and disk I/O. Just remember, disk I/O is very slow. Comparing with read and write with memories, right? And the complex applications streaming and interactive queries all need one thing that MapReduce does not have, which is the efficient primitives for data sharing. So this motivates us to, or motivates the researchers to create this so-called Spark. So what is Spark? So Apache Spark is an open source cluster computing framework for real-time processing. So it is a framework and it is designed for real-time processing. So Spark provides an interface for programming entire clusters with implicit data parallelism and fault tolerance. So Spark is built on top of Hadoop MapReduce, but it extends the MapReduce model to efficiently use more types of computations. So let's have a closer look at Spark. So the features of Spark. So Spark have a couple of features that distinguish it from Hadoop. For example, polyglot. So Spark provides APIs in Java, Scala, Python, and R. So different programming languages. And it also provides a share in Scala and Python. And speed. So Spark runs up to 100 times faster than Hadoop MapReduce for large-scale data processing. Spark is able to achieve this speed through controlled partitioning. It manages data using partitions that help parallelizing distributed data processing with minimal network traffic. And multiple formats. So Spark supports multiple data resources such as JSON, Hive, Cassandra. These data formats are different from usual formats such as text files or CSV or tables in DBMS. And the data source API provides a pluggable mechanism for accessing structured data through Spark SQL. And lazy evaluation. So Spark delays its evaluation till it is absolutely necessary. So this is one of the key factors contributing to its speed. Real-time computation. Well, Spark's computation is real-time and has low latency because of its in-memory computation. So Spark is designed for massive scalability, and the Spark team has documented users of the systems running production clusters with thousands of nodes and supports several computational models. Hadoop integration. So Spark provides smooth compatibility with Hadoop. So the Spark has the ability to run on top of an existing Hadoop cluster using Yarn or for resource scheduling. Right? And machine learning as a hot topic in recent years. So Spark's machine learning library is the machine learning component, which is handy when it comes to big data processing. So Spark provides data engineers and data scientists with a powerful unified engine that is both fast and easy to use. And for the ecosystem of Spark, so the left part of this figure is the 4 programming languages that we've mentioned before. So Scala, this is Java, Python, and R. So in our course, we will mainly use Python, so which is PySpark. And on the left side is the ecosystem of Spark. So first of all, we have the Spark core here. This is the base engine for large-scale, parallel, and distributed data processing. It is responsible for memory management and fault recovery, scheduling, distributing and monitoring jobs on a cluster, and interacting with storage systems. And Spark SQL. Spark SQL is a module in Spark that integrates relational processing with Spark's functional programming API. It supports querying data either via SQL or via the Hive query language. So if you are familiar with relational DBMS, then Spark SQL will be an easy transition from your earlier tools where you can extend to Spark SQL. And Spark Streaming is the component which is used to process real-time streaming data. Spark MLlib is the machine learning library used to perform a machine learning in Apache Spark. And this GraphX is the Spark API for graphs and graph parallel computation. Finally, Spark R is an R package that provides a distributed data frame implementation. It also supports operations like selection, filtering, aggregation on large data sets. So that's the core part of the Spark ecosystem. In this course, we will mainly focus on Spark MLlib and Spark core here using PySpark. But we will also introduce Spark SQL, Spark GraphX, and Spark Streaming. So let's look at the Spark architecture. So first of all, the master node. So this is the master node. It takes care of the job execution within the cluster. In your master node, you have the driver program, which drives your application. The code you are writing behaves as a driver program. So inside the driver program, the first thing you do is you create a Spark context. So the Spark context is like a gateway to all the other Spark functionalities. It is similar to your database connection in your 9311 course. So any command you execute in your database goes through the database connection. So anything you do on Spark goes through Spark context. And the cluster manager, which allocates resources across applications. So the Spark context works with the cluster manager. The cluster manager could be either Spark's own standalone cluster manager or Yarn from Hadoop. So a job is split into multiple tasks which are distributed over the worker node. So this is the worker node. The job of the worker node is to execute the tasks. The tasks will be executed on the partitioned RDDs in the worker node and hence returns back the result to the Spark context. We will discuss about RDD later. But once connected using a Spark context, the Spark acquires executors on the node in the cluster. executors. And so the executors are processes that run computations and store data for your application. So if you increase the number of workers, then you can divide jobs into more partitions and execute them parallelly over multiple systems. So it will be it will be faster, of course. Alright, so this is pretty much all for today's lecture, but I will spend a couple of minutes on lab 1, just to give you some instructions about that. So basically, lab 1 is about to set your programming environment for MapReduce. So I have to say that there are 4 labs in this course. Well, we don't give any scores for all these 4 labs. It's just for you to get familiar with the programming environments and some contents from the lecture notes, and will help you on your projects. So that is the purpose of labs. And I have to say that lab 1 is kind of compulsory, in the sense that you have to finish it to make sure that we are all on the same page. By we, I mean you and the teaching groups, me and the tutors. So then your submissions of projects can be run correctly on our side and on your side as well. So basically the introduction is kind of in detail, step by step, from install JDK to Python Anaconda and Notebook, set the environment, install PySpark, install Spark and Hadoop, link the environment with the notebook, and also the test your environment. So basically, if you can correctly run this part of code without any error, then you have complete this lab. And more importantly, I think basically your environment is set to be correct. It is possible that you will face some difficulties when you do lab 1, and it is possible that for whatever reason your machine just cannot output the correct results. I mean, usually it throws an exception. Yeah, all these are possible. So what my suggestion was, I highly encourage you to discuss all these kind of issues on Piazza. Okay, and I also encourage the whole class to help each other. The teaching team has put a lot of efforts on making this lab specifications. We have tested the lab on our own machine with Linux, Windows, and Mac OS X. But still, I mean, it is possible that you are facing some strange issues that we have not seen before. So raise your questions in Piazza. If you know how to solve the problem, help your classmates. And besides the Piazza, I do suggest you to search your problem or search your issues in Google and use the online forums such like Stack Overflow. usually there will be exactly the same or at least similar issues to yours, so which you can borrow their ideas or see how they solve the problem. So in one word, try to get all these things done by week 5, and then you can start hopefully I think 90% possibilities we will release the project 1 in week 5. So yeah, you can get prepared for the project. Oh, and one more thing. I mean, when you ask the questions on Piazza, do mention your operation system. Okay, so different operation systems could have different behaviors, and who knows? I mean, yeah, you gotta let us know what operation systems you are, and also what's the problems. All right. So yeah, that's all for today's lecture, and see you on Wednesday.